which characterizes such transforms of positive measures, namely is the theorem of Bernstein. Saying that necessary and sufficient condition is that if we restrict this function on the positive semi-axis, this is completely monotonic. If in addition we have the rapidly decreasing condition, this function will be of plus infinity on the closed semi-axis as a function of x. And completely monotonic, will return to this shortly, means that the derivatives alternate. You can imagine here, zero derivative is positive, I take one derivative, it pops negative, and so on. And the interesting part that this is a characterization. It's due to Bernstein, a very beautiful result. And what is more interesting for us, we discussed uniqueness last time. So let's see how do we recover the moments of the measure. From here. Well, obviously, we take a number of derivatives, and instead of z, I have t. It comes out to the respective power, so will be nothing else than the derivative of any order of the Laplace transform. So, uniqueness is equivalent to quasi-analyticity. Yeah, for the Stiglitz. So all the power of the quasi-analyticity as we encountered last time applies and gives you necessary and sufficient conditions, as we saw in the work of Kagerman in particular. Today we want to go not so much into the uniqueness problem, but into a transform which is very appropriate to extend this to several variables. And I'll do a very simple computation. I start with the Laplace transform of the measure. And I'll put it at a point p times t. And I multiply this to minus p naught t. So I do another Laplace transform with p naught positive. We have rapid decay at infinity, so the convergence is not an issue. Therefore, I can revert the order of integration.
The audio is very stable. So this, I can place this on there. This will receive it. Comes on it. And it is. So this could be listed as G.
Yeah, you agree with me. And we get, of course, this is computable. At infinity vanishes, all quantities are positive. So at zero, we get exactly the fraction. And the result will be this integral. So we recover essentially the Stieltjes transform by operating twice a la Laplace. P? P is a fixed positive number. So this is a Stieltjes transform we had before. And this is the way we'll go into several variables. This is called the Fantappie transform. And it's a little special because now in the denominator is homogeneous in P naught and P. And this is a big deal, so we can go into the projective space and so on. And has very special properties. This is the way it was developed by Luigi Fantappie in the 1930s into several variables. This will be just the inner product. And our story starts here.
Is the 20-second delay going to affect this? The audio will be 20 seconds late. It's good.
So we'll do the basic properties of this transform in several variables. The Bernstein type theorem holds, and I'll explain exactly the setting. Then the inversion is an issue. How, of course, for the Laplace transform, you know, there are several inversion strategies. The question is, how do we invert this in several variables? It happens that this transform has very good positivity properties, better than other transforms in several variables. And in particular, it implies famous analytic duality phenomenon. And for the second part of my talk, I'll speak about the multiplicative structure behind this transform. If we see the measure as an additive, let's say it's a sum of point masses is just a rational function with some denominators, has also a multiplicative structure, and that was developed by Andrei Markov, the same Markov you know for the moment, and has a remarkable property. So that's a number. And to this, I'll start with mathematical economics. So we have a positive measure as we discussed, now in the positive octants rather than the semi-axis. And we consider P naught the price per unit of a production of a factory. P are the prices of the factors which enter into this production. And they are characterized by technologies, by a vector which runs over the first octant and is distributed according to this, let's say, probability measure. So if we want the profit, we have to take the positive part of the price minus the cost. And this formula is very well known to economists. And is asking, okay, if I know this for enough many values of P naught and P, can I recover the distribution? Is this unique, the distribution with this production function? And so on. So, exactly what I discussed before, but now motivated by a very clear optimization problem. Besides that, can we characterize all these transforms? If I give a positive measure on the octants, is there a characterization? Is there a label I can put on them and see whether they are pure or not? And, of course, the reconstruction. These were rather recently solved by Gennady Henkin and Shanani and these questions, and the solution goes as follows. You remember the production function. If we take in the sense of distributions the derivative with respect to the cost, we end up, and let's assume that we have, so that we don't run into heavy distribution here, but we have a density for this distribution. We run into averaging our probability distribution on a sublevel set, on a semi-hyperspace. And if we take a second derivative, as you know, just basic calculus, take the derivative with respect to P naught, we get precisely the Radon transform. That means we average this test function, this density along hyperplanes, and we label this by the slope and the distance from the origin. So this is exactly the Radon transform. Well, nothing surprising. If we simply take this integral with respect to the tau parameter of the second derivative is the Laplace transform of the measure. So these are very basic computations. Therefore, the Fantappie transform will be one more time the Stieltjes transform now of this second derivative. So we land here to the analog of the integral transform I mentioned before. Now P is a vector in the octant. P naught is a positive one. This is called the Fantappie transform. And the solution to the problems I just mentioned is rather classical. The uniqueness follows from the uniqueness of the Laplace transform. If we assume some decay at infinity, then we'll have analyticity, of course, not in the half space. You have to imagine the octant, and you have an analyticity in the tube domain over the complement of the dual octant. We'll go to that very soon. And therefore, we have unicity. The inversion is challenging if we want to remain just to real values. Think a little to the Laplace transform. As you know from complex analysis, how do we invert usually Laplace transform? You take an integral in the imaginary domain. Well, if you want to stay only on the axis, there are inversion formulas. Post was the first to do. Then Wheeler has another. And you can return to the distribution from averaging from some interpolation problem only on the line. And this is also valid here. So it's a little more challenging. So the definition. Now, rather than the octant, we take an acute convex solid cone. That means it has interior points. The dual cone is defined this way. We are in Euclidean space. And we consider a positive measure of finite mass supported on this closed set. Yeah, it can have point masses on the boundary. The Fantappie transform is precisely what we expect. It's exactly this integral on the dual where the measure exists. And the denominator is homogeneous for degree 1 in the coefficients. So that's quite good. What was surprised before, P naught has to be positive so that this doesn't vanish. We are with P in the original cone, with X in the dual, so this is non-negative, and we consider only P naught positive. So it's the true analog of the Stieltjes transform. And the relation to the Laplace transform is exactly what I did in 1D before. It's very clear. So we do iterated Laplace transform and we end up analyticity.
So, questions.
Yes, please.
So, I mean, since we end up with something that's homogeneous, you keep saying you iterate the Laplace transform, but actually we take the first Laplace transform, we also do a scaling and then we apply.
Yes, of course. Yeah. So it's a double Laplace transform.
Right, a double Laplace transform, but there's also a scaling transform.
Of course. Yeah. So and I stress this, thank you for asking, the homogeneity in the denominator is quite essential. Now we extend it to several complex variables. So obviously, if I take the real part of the vector u, now we are in Cn or in CD, in the interior of the original cone, and if I take the real part of u naught strictly positive, this remains homogeneous but now in the complex domains. And this transform will be what we call the tube domain over this convex cone. So we end up with a setting which is well known to complex analysis. A tube domain is such a tower over a convex cone. And what it is very special, it has a very rich group of biholomorphic automorphisms with a homogeneous space. And therefore it has a rich harmonic analysis. My colleagues here in complex variables approve. And this is something remarkable because now we can connect with the analysis on tube domains. A second important feature I mentioned briefly is that if I start with the positive measure, the real part of this transform, so we are now over the tube, is non-negative. Well, that's something, a big desire in function theory and in operator theory, to produce as many functions with positive real parts as you can on such domains, on such homogeneous. And that's non-trivial, because if you take all other transforms known in complex variables, Prof, Martinelli, Cauchy, Enkin, and so on, they don't have this feature. So we'll explore this. Now, the Bernstein theorem runs as follows. Let's go slowly. We start with the acute convex solid cone. And we consider a function which is C-infinity on the interior of this cone product with the semi-axis and continuous on the boundary. This function is the Fantappie transform of a positive measure on the dual cone if and only if, very simple conditions, is homogeneous of degree -1. And is completely monotonic. If and only. Now, the proof has a long history. It went to Bochner. Gilbert has essentially the full proof. And the adaptations to what I'm telling you here, to all kinds of growth conditions of the measure are due to Henkin and Shine. So, essentially, Bernstein theorem, one word holds with some. Good news for the connoisseurs, we can impose complete monotonicity separately in each variable. And we don't have to take the points where we sample these derivatives on a continuum, but can be a discrete set, so that all entries, all coordinates are under infinity. So there is a discretization here, which for applications is quite useful. That complete monotonicity is equivalent to separate complete monotonicity, and the complete monotonicity is enforced only on a sequence, on a discrete set. The inversion, that's a challenge. And I'll only put you for information the formula of Mitter, the one which uses purely real arguments, so you don't go into the complex domain at all, no Cauchy formula, nothing, is this one. So in one variable, the inversion goes precisely for the Laplace transform, goes precisely like this. So you sample the Laplace transform and its derivatives only at the integer, only at lattice, and you take the sum until the integral part of x. Believe it or not, is in the Wheeler proof, we know it. This converges, this gives you the density of the original function. It's quite remarkable. Was forgotten because computers until recently could not do these computations effectively. But now it's rather accessible to computations, and this is, if I understand from Shannon, this is the way they invented the transform. Here are the references. It's a very beautiful piece of paper for the experts here in the room or listening. Has a lot of side remarks which are, I don't think, completely exploited. And I strongly recommend it. Shanani continues to work on this and has several articles more oriented towards economics. So in particular, just to wrap up a little this part of my talk, we have a rather effective way to invert the Fantappie transform, and we know quite a few of its qualitative features, like positivity and recursion. Now, there is much more. Fantappie started with this transforming several variables in the 1930s. And there is quite a glory since then. And only recently, I'll show you towards the end of my talk, new and very surprising aspects of this came out. So it is a concept which went up and down many times and found always some solid ground in different areas. Analytic duality. Let's change a little the setting with minor modifications of the parameters and consider for the time being the Fantappie transform in a domain in CN, in Hermitian space rather than Euclidean space. So we take a measure with compass support, now in CN. And let's define rather ad hoc, is not exactly what we had before. The Fantappie transform normalized to be this transform. So it's not the Cauchy kernel, it's not the Bernstein kernel, it's a universal kernel good for all dimensions, doesn't depend on the dimension. Define on the vectors, this should be C again, which have the Hermitian product different than 1, so that the denominator doesn't vanish. And this is, of course, related to the Laplace Fourier transform as we saw before. There is no surprise here. Yeah, if I take first the Fourier Laplace transform, this is compact support. So this converges, and I get exactly the Fantappie tensor.
So what's W star?
CW star is just the inner product. It's the Hermitian product. I simplify a little the notation.
Is it addition or non-addition?
Say again.
Addition or non-addition?
Hermitian. Of course, you can define it with non-Hermitian product, with a bilinear. This is Hermitian. And here enters Fantappie with this big dream. First in one variable, and then I'll show you second. Let's consider analytic functions defined in a neighborhood of the compact set K. And let's apply to them a linear continuous function. So I want a characterization of this linear continuous function. If you want the topological dual of this space is rather complicated. So it's an inductive limit of Fresnel spaces, so you have to take the topology and so on, and the linear functional. Fantappie says the following. Let's apply our functional to the kernel. And our setting will be just the Cauchy kernel for the time. And we call it after K the indicatrix of the linear function. Of course, this is an analytic function defined on the complement. Clearly, if Z is outside the domain, Z minus the point on K doesn't vanish, so this makes perfect sense. Because the functional is continuous linear, the dependence on the parameter Z is analytic. So we end up with an analytic function on the complement. Maybe I should make a drawing here. We have a compact set K. We consider analytic functions defined in a neighborhood of K, and the domain depends on the analytic function. And we take this transform. It will be analytic in the complement. And of course, if this L is continuous, when Z goes to infinity, or on a compact set, the value at infinity is 0. Now, if we take an analytic function here and write the Cauchy formula for a system of curves which surrounds K, we have precisely this representation by applying the linear functional. We obtain a pairing between the analytic function defined in the neighborhood and the transform, the indicatrix. This is homotopy invariant for the system of curves we are choosing. And it gives a non-degenerate pairing, which is even continuous. If we consider the Fresnel topology on the complement, and I put here functions which vanish at the point of infinity. Well, this is a theorem which is attributed to Koethe. Grothendieck has accounts to this duality, and is quite substantial, quite famous, because it gives you a characterization of linear functions in terms of analytic. Well, not surprised. This extends to several parameters. I'll show you a proof here which is a little ad hoc, but is related to some operator theory, we'll see a little later, which goes as follows. So now, rather than working in C, we take the Hermitian space convex bounded domain. And we consider, as before, the germs of analytic functions on the closure of these. And the analytic functions on the dual of it, let's call it the dual quotation. So is the domain defined this way so that the Hermitian inner product is different than 1. The theorem will give us in the end playing, and I'll go back to this in a second, will give us the identification of the dual. This was done by Martineau and Heisenberg. It's exactly what Koethe and Grothendieck did. And the proof goes as follows. This is why I was searching. So what they say here is that the germs of analytic functions there and the analytic functions there are in topological duality, and is established by the Fantappie transform. Now, for the experts, we take an exhaustion with convex sets, and we can assume that the duals all contain the ball. That's a very important observation, and I'll make it clear now. So we deal, the denominator is something like this. What is this? Is a quadratic form, is a sesquilinear form, which is the polarization of the equation of the ball. And what we do in this duality, it's exactly the duality between pole and polar in projective geometry. Namely, in one variable, the real variable, if we take a triangle here, what will be the dual? The polar of this point is the tangent. Here we have the tangent, and so on. So the dual will be precisely this triangle. So automatically, when we work with the Fantappie transform, this geometric interpretation, the polarity with respect to the unit sphere is intrinsic. So we do an exhaustion and related everything for the expressed to the Bellman space, and then the proof comes rather easily once we identify the Fantappie transforms of functions which are in the Bellman space. I'll not go into full details here because I know not everyone is familiar with this space, but it is essentially the standard proof of Martineau and Heisenberg theorem. What it is special in this setting is that we have the pairing, which gives us the duality. Written on power series is precisely this one. So we have a factor here, weight, which is nothing else than expanding this into a power series. And we have this very nice scalar form which gives us the duality. I'll give you references. Now, important issue. Before we worked on wedge in Euclidean space, nothing was lost. If we work with the Fantappie transform in the complex domain and we take only complex values, quite a lot is lost. Specifically, we cannot reconstruct the measure from this transform. Consider just a big circle on the sphere. And average the Fantappie kernel along that. Of course, will be the value of Gauss mean value theorem, will be the value of the function at the center. And this is one for all big circles on the sphere. So we do not expect to have the full measure from these values. Still, it is very, very useful. Now, as I mentioned, one of the big issues in potential theory in multivariable is to understand the structure of positive pluriharmonic functions. So these are analytic functions. Let's say we stick to the board. Functions which are analytic, complex analytic in the unit ball in Cn, and have non-negative real. Big open question. This is a complex cone. Which are the extremal waves? Nobody knows. A lot of people pass by here. The Russians call the American, the French. There are observations here. Frank Forelli essentially spent a whole career on that. Rudin and Alexander in St. Petersburg and so on. We don't know. But to understand this space, so this is a convex cone in space. It's very useful to consider Fantappie transforms of positive measures on the sphere. And we normalize them with the full measure here, the total mass, and an arbitrary parameter on the imaginary axis. This is called parallel, if you know, is the Herlotz transform. The real part of this in one variable is the Poisson kernel. So this is a very standard transform in complex analysis. So we take this. So it's a minor modification of Fantappie transform. And we produce, as we had before, a lot of functions with positive real part. The question is, how many do we have? And the surprise, this came quite late, is that this is a dual with respect to our pairing of this unknown complex cone. So if we take our pairing and define the dual polar, if you want, by this inequality, so this is the polar cone, the polar of pluriharmonic, non-negative pluriharmonic functions is exactly the Fantappie transform of positive measures and vice versa. So this is quite remarkable. It's a joint work with John McCarthy and has some operator theory implications. Now, I'm not going to deep waters. Delta is not here, but hopefully you will see this. This is very exciting because you can realize now this Fantappie transforms in a Hilbert space rather than just working with measures. Forget about measures and work with operators. You take what is called a spherical contraction. So an n-tuple of operators commuting which satisfies this identity. And then the analog of the Fantappie transform is precisely this. So you take the linear pencil resolvent, apply it to a vector, and you get exactly the. Atapale, an Indian professor, who proved that these are always subnormal. So that means there is a measure somehow lurking behind giving a representation of these operators. And from here you derive quite a lot of interesting features for transforms of Fantappie transforms on the board and operator theorem. Just for your information, you take the Fantappie kernel and you treat this as a reproducing kernel formally. This will produce a Hilbert space, which lives on the unit ball, analytic functions in the ball. They are not Bergman, they are not Hardy, they are a little different, but they are very special because this is the universal reproducing kernel on which you can do bounded analytic interpolation. The original bounded analytic interpolation was done in the unit disk by Nevanina and Ick. And quite recently, Jim Adler and John McCarthy proved that this space, so this precise reproducing kernel, gives you the universal one. Any other one is a pullback of this by some analytic transfer. This is quite substantial. Therefore, the study on this space, the multipliers and so on, is in order. And this continues to this day to be done. There is quite a big group of people interested in it. I'll give you only some references. So maybe then we take 7 minutes. So, the linear convexity done by Heisenberg. Then there is a very beautiful book which exploits the Fantappie transform and convexity in the projective space. Interpolation is related to the Fantappie transform in this article of Mats Andersson and the late Mihai Plasarev. A very readable and almost of a book size, a survey on the Drury-Jacobson space, this reproducing theorem, remains on archive, by Michael Hart. It's quite recent and is interesting. There is a lot of activity here. And our so I will take a short break and then we turn the page.
Questions at this point? Okay, so let's thank Mihai.
Check. Check.
It's coming.
Check.
No, it's coming.
Check. Check.
So it was 15 minutes late, and the professor was also watching from some other country.
Check. 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 Check.
You used something there, no? A big mic that captures the whole room's audio.
Yes. Check.
This was better than that. This one?
This is.
No. This is always better, but I'm asking you.
Check.
Okay, so we can continue.
ಆ ರಿಸೀವರ್ ಎತ್ಕೊಂಡ್ಬಿಡು
Single fractions. We can start.
ಯಾ ಜಸ್ಟ್ ಅ ಸೆಕೆಂಡ್ ಐ ವಿಲ್ ಗೋ ಲೈವ್
Okay, so we start on.
ಯಾ
Okay. So why I'm calling this a multiplicative theory, because if we start with finite to take an exponential of the generating series and look at the resulting coefficients. And his observation, exactly the same year as Stieltjes proved the big memoir, is that you have a positivity condition built in, exactly the moment condition for an arbitrary measure in these coefficients. Just for your fun, 1896 was the year. This is the article in Mathematische Annalen. And the condition is the measure it has weights between 0 and 1 if and only if the respective power series has a non-negative Hankel matrix. And second is this is determined by finitely many moments if and only if this Hankel matrix is the general. I'll spend some time on this finite determinateness because it's an important feature we'll exploit in several variables, including in the lecture next week. And here is his theorem. At that time, positivity was not on the list, but rather continued fractions. So he says that this kind of continued fractions were already employed by Stieltjes in his famous memoir, and says that the exponential transform of the Cauchy integral has a continued fraction. I didn't print out the next page where you have positive entries. So it's exactly the positivity we are using. And in the case of finite determinateness, this is a rational function. And we know by now, we discussed a little in the last lecture, how from this rational function to by the Pavlet approximation scheme. Namely, the continuous fraction expansion will finish, and you have all the data encoded into a number of free parameters. So that was the discovery of Markov. Let's do the simplest verification. I take the Cauchy transform of the unit mass between A and B. Z, let's say, is in the upper half plane. I can integrate using a branch of the logarithm, and this will be the exponential of the logarithm. And the respective rational function is precisely 1 plus a point mass at the point at A, a weight, and again the Cauchy transform. So it's exactly what we encountered before. The exponential of this density, extremal density now, is precisely of this form with a point mass at A. Now think that you take sum of disjoint intervals. This will correspond precisely to a product here. And therefore we have immediately will expand this very briefly later, we have what I mentioned here, the multiplicative structure of an additive Fantappie transform. The point I want to make is that this extends to several variables very successfully, and it gives you quite a lot of information about the Fantappie transform analogy. Now, the recognition came a little later by a Hüser and Mark Krein in about 1 year interval. They are all written in German, and they were at the time in Harkov. Now Harkov is in the news these days. Hard times, but 1934, 1935, if you know a little the history of Ukraine under the Soviet rule, was also a very harsh time in Harkov. So they recognized the importance of Markov discovery, and they wrote these 6, one after the other articles related only to the Markov transform, what we call it now. And they are extremely beautiful. Now they are contained in a book, and I warmly recommend you to have a look. Called The Markov Moment Problem and External. It's translated and is very accessible to non-experts. The point being that so far we worked with power moments, but we can expand in Chebyshev, in I don't know, wavelets, in trigonometric functions and so on. So it's rather general. And I'll tell you the big picture as was revealed by Mark Krein in this, and then we'll return to the transform. So let's suppose that we have a ground measure can be measured on a bounded domain, can be the Gaussian load, but not supported by a zero set of a polynomial. So that's the polynomials we are in Rn are contained in the one. So let's suppose we are with the Lebesgue measure in a screen. And there, I want to understand, to reconstruct a shape function. I switch a little the setting of Markov with the weight between minus L and L fixed. Why I call it a shade function? Because I consider the minus L white, L black, and all colors are in between. So think in two variables that you want to encode and to understand the picture with color picture. And the first question, when is this determined? By finitely many of its moments. Very basic question. We encountered before determinateness when we go to infinity. Here it's a finite section. We are with multi-variables. And we go as follows. So we have the shade, the moments of the shade function. Obviously, this is complex. It depends on the measure. The measure is between the weight is between minus L and L. It's a complex set. It's a closed complex set in a finite dimensional space labeled by all multi-indices of length less than. Any linear functional on this space is acting as follows.
Didn't that mic work?
If a polynomial,
But the sound is very poor. Same like last half, first half.
the linear functional on the respective
Maybe you
moments
can
will be some
reduce.
coefficients which appear in the polynomial attached to the linear functional, and it represents the integral. Nothing surprises the linear function. So, this is bounded by the integral, which is obviously the L1 L infinity norm, less than L times the one norm of the polynomial which represents the function. If this, so maybe I should make a drawing here. V is the space, and here is the set of all these moments between minus L. If the point falls inside this ball, in the interior, it means that any functional which separates this, which is, let's say, non-negative or bounded by the respective norm, is strictly less than the value, the maximum value, the optimal value. Therefore, this is not determined uniquely by the moments, because being in the interior, the supporting functional is here, will have room into the inequality. In other terms, if you don't like this, the extremal situation is only when the equality sign in the L1 L infinity estimate is achieved. And now this is very clear. Mu is a positive measure. L is fixed. This is the integral of the norm of H. So necessarily, G, the shade function, has to be equal to the either L or minus L, if there exists such a H with this norm. Conclusion for this very simple convexity observation. The only pictures which can be exactly determined by finitely many elements are black and white. And moreover, the respective polynomial which describe the linear functional is given the shade. This is black, this is white, and this is the zero set of the polynomial. So they are necessarily black and white, and the boundary between the two regions is given by a single polynomial. That's quite a discovery, and this was done by Krein following the researches of Markov. It's very simple convexity, and I invite you to just consider this space of moments, what means a linear functional there, and you will see immediately that the constraints we put on the weight represent an inequality for the function. And that means that you have a supporting equity. We can, of course, normalize this to the original question. And therefore, we have this, I call them principal subalgebraic sets in this setting. And they are the only ones which can be determined by finite exercise. Let's take the first order times, and the one, and it's the opposite, x, y greater or equal than 0. This is given by a single polynomial inequality in the square or in Rn. This is not. Proof that you cannot write this as a single polynomial inequality. It's a nice exercise. Then the conclusion is quite remarkable that if you take the first octant, there exists a measurable function different than the characteristic function, which has all the moments up to a fixed degree. And there are infinitely many like this. And on the other hand, if you take the opposite octant, there exists only one. Simple complexity theory. Now, there is much more here. Markov exponential transform entered very heavily into operator theory. So I switch a little setting, and I'm asking the following: how is the spectrum of a self-adjoint matrix changing when you add the rank 1 perturbation? You have an interlacing of the eigenvalues. That's, for instance, proven by minimax. And if I consider now the shade function, the G we had before, just this union of characteristic functions, maybe I should make here a drawing. So this is the spectrum of this is the spectrum of the vector. We take these intervals and we run the Markov transform. The so-called perturbation determinant, the quotient of the two resolvents, has the following determinant, obviously, which, as we saw in our simple exercise, is the exponential of the sum of these intervals. For each interval, we have the respective fraction. But on the other hand, immediate linear algebra computation, the determinant of A minus Z inverse times this is the identity plus the resolvent against this rank 1 vector with which we did the computation. And this you expand with an orthonormal basis starting with this is precisely 1 plus the resolvent estimated at this vector. Now the operator has a spectral measure, and this is the Cauchy transform of that measure. So what we get here is the exponential part, and here the additive part, in 1D. This goes very far, because you can estimate now the trace of the functional calculus, let's say with a polynomial between these two, the operator and the perturb one. And this is precisely given by the derivative, depends on the derivative of P, and the so-called spectral shift function. And this is exactly the extremal solution to the moment problem. My lecture Monday will be exactly on the spectral shift and what can we do in two variables with it. So this is why I mentioned it here. Now, exercise for your analytic geometry students. How do you produce interlacing points on the line? Take an ellipsoid. It has principal semi-axis in any number of dimensions. Intersect this with a hyperplane, with a real hyperplane, passing through the origin. It has, of course, -1 number of principal axes, and they are interlaced. Try to prove it. That's Rayleigh theorem. Yeah. And it's very much related to what I mentioned before. So I'll show you how we do with the Fantappie transform. This is work I did with a student at the time. He is an engineer, and we were interested in, we call it regularizing a very bad measure by a phase by this shade function we had before, which is bounded. So rather than working with a very bad measure, you do an exponential transform or logarithm if you want, and you end up with a measure which is much better suited for, in this case, for entropy estimates. And the result is as expected. There is no surprise here. We exploit the harmonic analysis on the tube domain. So there exists a Herlotz kernel which gives you precisely the phase. And the function, the respective one, is precisely entering into this. So this is a universal kernel, and this is the phase. And here is what is known. We use, of course, the Hardy space on the tube domain. The reproducing kernel is very simple, is well known. And this Herlotz kernel is precisely this one. And this works quite magic for quite a few examples. For instance, on the octant, this is well known, is the Seger kernel of the octant. And again, this gives us precisely the form of the Herlotz kernel. And we obtain, for instance, in D1, a well-known representation of the Herlotz. I don't go into the detail. I just show you that this can be done, and it was useful to do entropy estimates for moment problems on wedges. The verification is rather simple, and in one variable we get exactly what we know from Nevadina. Before we go to the measure, because I mentioned this, I have to give you one account. Why do we expect this exponential representation? So from the function point of view, function theory point of view, we did the following with a function analytic in some domain, which has positive imaginary part. Let's work in one variable in the situation discussed by Mihai. So, this function takes the upper half length itself. If it is not a constant, will never be zero in this open domain. If it is not zero, this is simply connected. The logarithm exists. Simply connected domain, non-zero. I can speak about the logarithm. Now, the logarithm has a real part. And an imaginary part. What is the imaginary part of the logarithm? Is the argument. Where is the argument in the upper half plane? Between 0 and pi. But this is good news. It means that the logarithm is a function which has a bounded imaginary part between 0 and pi. Can I write this specifically as a Cauchy integral? Yes, I can. It's the Poisson kernel, so there are boundary values. And this is precisely the phase. When we let the imaginary part of the logarithm of f of z, let's say x plus I epsilon, tend to 0. Almost everywhere, this will be a function which is between 0 and 1. And there is a standard formula, I will not write it, which the Poisson formula, which gives you the function in terms of imaginary part. And once you have that, it's exactly what we expect, that f of z will be the, if we normalize this at infinity to be 1, is precisely the exponential of 1 over pi, the integral of phi of t minus z. That's the Nevanlina representation. Here we have our function. The Fantappie transform is here, is 1 plus the Fantappie transform, here is exponential. So there is no mystery here why we have a phase which is bounded. And the relation between the original function and the phase is the whole game with the Markov transform. He understood very well that and put it at work in different contexts. And we saw it in particular on this shape reconstruction. So let's turn the page, we have some time. And take some simple examples. We are in Euclidean space with a simplex. And there is an important probability distribution which has precisely this weight on the simplex. So here are the gamma functions, tau are some probability in there will be positive values which add up to 1. And the interesting part here is the beginning of the story. The Fantappie transform of this measure has a closed form. So it's not rational, but is a fractional power of a simple fraction. And this gives us an idea and was exploited rather recently. I'll give references immediately into the so-called Markov Krein correspondence. So if we start with measure sigma, in particular our point masses at the edges of the simplex, and we integrate against this logarithmic kernel and take the exponential, we get exactly the Fantappie transform of another measure. And this is called the Markov Krein correspondence. We start with sigma, we end up with mu. This goes far. Sergei Kirov, he is no more among us, a very talented Russian mathematician, discovered with his student the following. If we have probability measures into the Markov Krein representation, and we push forward the measures by an affine transform. For instance, we take the marginals, or we do some simple linear and translation information. This carries over is functorial with respect to the transform. The Fantappie transform of the push forward is exactly the multiplicative transform of the push forward. And this apparently has big consequences in probability theory and combinatorics. It's subjective. So for any probability measure, there exists a probability measure entering here, but is not defined everywhere. We don't have, for any probability measure, such a representation. So let's discuss very briefly the probabilistic interpretation, which is quite fun. It's random variables over random variables. We fix some points on the positive semi-axis, and on the simplex with the coordinates P0 up to Pn, we consider the Dirichlet distribution what we had before. And we take a discrete probability measure with weights pk supported by the points xk, distributed according to mu. So essentially we take the interior of the simplex, and for every point we have such a probability measure. Now, the distribution of the mean of these fields of probability is exactly the Markov Krein transform of the original point masses at the point x. This is quite remarkable and was exploited by, I think, Percy Diaconis for a continuum, and is quite an important issue in probability. So this Markov Krein transform, which contains the Fantappie transform, represents exactly the average, the mean value of this probability distributions. So it's, if I understand, it's a random variable over random variables. And there is a classical in 1D formula for the distribution of this. Namely, if we start with tau, point masses or not, this is precisely how you compute the Krein Markov transform. What about complex variables? Let's take a simplex now. We fix a number of points in Cn, and we take the simplex with these vertices, and we consider the integration of an analytic function, on an entire function, let's say, on this simplex. So this is simply the average of the entire function on a simplex embedded in a complex space. This is an analytic function, obviously, and we can define, according to this, in the sense of distributions, this derivatives, this analytic function. It remains an analytic function. And hold your breath. The Fantappie indicatrix of it is precisely this product of simple fractions. So it gives you precisely the hyperplanes in the denominator, which identify the vertices of the series. So again, the Fantappie transform is very clear here, applied to an analytic function at this time. Splines can be obtained this way. I'll give you a couple of examples and I'll finish. We have point masses, and we consider just the sum of the Dirac masses without any weight. And then, of course, the product will be this one. And the weight entering into the Markov Krein representation, this is 1D, is this spline function. You know, piecewise polynomial. Cauchy's measure is invariant. That's quite remarkable. That if you take the Cauchy measure, 1 plus x squared, the arctangent, in this representation, it stays is an eigenvector. It stays the same. References are here. Jacques Farreau has an interesting, rather long paper exploiting this for orbital measures of groups, the Markov Krein transform. Kerov has ample survey where he discusses probability but mostly combinatorics, and is very, very interesting. And this is in several variables. What I mentioned is a short note, but also full of ideas. So everything what I showed you is related to the Fantappie transform in different impersonations, as we can see. It enters in duality, in probability. I didn't touch combinatorics, didn't touch operator. So time to wrap up is Friday afternoon. This is the book of Fantappie, written not in his mother tongue, but in Spanish, published in Barcelona. And it's quite interesting because he lists here the principal articles where he developed the idea. By the way, the idea goes back to Volterra, but he developed this. So the analytic functionals, yes, called 1930 starting, and then it goes on up to 1941. And his dream was to use this transform for solving the Cauchy problem for hyperbolic equations and in closed form. And he was able to do this quite far. And is this last article, and then after he published the book, he had more contributions for hyperbolic PDEs. Here is a definition, which is the first appearance of this transform. So he calls it the linear analytic transform, the projective indicatrix of the functional. Not necessarily an integral, that's the interesting part here. It's functional, not necessarily coming from a measure, and is here, and then he puts it at work. It's an interesting text. Now, he is famous, just a few words before we go. Fantappie is famous for the idea of syntropy. You know entropy, the degree of disorganization. He said that life should be based and have principles, mathematical principles, on a syntropy, which goes into the organization direction rather than house. And the idea is still alive, and there are groups of biologists who bite into this. Don't ask me more, but look, and it's quite interesting to see. He was a very open mind, and why not? Maybe there is no verification, there is no lab work which provides support for syntropy, but anyway, it's an idea which he had it. Now, his life was quite complicated because in the 1930s, he was sent from Italy. He was a famous professor there, already distinguished, was a colleague and a good friend of Fermi in Pisa, was sent to Brazil to build the mathematical education there. And this was a time of right-wing government, so was somehow representative of very right-wing government going to Brazil. And what is interesting, if I understand, is this article which I recommend, is that he fought hard for the purity of mathematics, for the professionalization of mathematics and its autonomy from engineering. At that time in Sao Paulo, the engineering was everywhere and mathematics was somehow embedded into engineering. And in this year of tenure as representative and director and leader of this, he founded the mathematical school in Sao Paulo, and he separated it from engineering, starting with the textbooks for middle school and going to high school and university and so on. So he deserves some credit, and we have to keep in mind that his concept is still quite vibrant, quite active. If you look at these recent works of the probabilists and combinatorialists, the Fantappie transform appears there in an essential way. So I'll stop here. Thank you very much.
Any more questions?
Markov chain is the same Markov.
Yeah, so I'm saying that whether this transform works better than Fantappie for certain cases.
I don't know exactly the origin.
I see.
I think they were independent. There were two independent ideas, and at a certain point they met.
I see.
Yeah, thank you. So the next topic is on redness.